Welcome to ReLU Radio, the podcast where we unpack the latest and greatest in machine learning research. I'm your host, Adam, and today we're diving into a fascinating paper titled Understanding Reinforcement Learning-Based Fine-Tuning of Diffusion Models, a tutorial and review from researchers at GeneTech, Princeton University, and UC Berkeley. Joining me to break it all down is my co-host, Eliza. Welcome, Eliza.
Thanks, Adam. I'm excited to discuss this paper. It's a comprehensive look at how reinforcement learning can be used to fine-tune diffusion models, which is a hot topic in the 1050th world right now.
Absolutely. Let's start with the core concept. Can you give us a quick overview of what this paper is all about?
Sure thing. This paper is essentially a tutorial and review of methods for fine-tuning diffusion models using reinforcement learning techniques. The goal is to optimize these models for specific downstream tasks or reward functions. For example, you might have a diffusion model that generates images, but you want to fine-tune it to create images with higher aesthetic scores or better align with human preferences.
That sounds really interesting. Can you break down what diffusion models are for our listeners who might not be familiar?
Of course, diffusion models are a type of generative model that's become really popular in recent years. They work by gradually adding noise to data and then learning to reverse that process. It's like slowly turning a clear image into static and then learning how to turn that static back into the original image.
Fascinating. And how does reinforcement learning come into play here?
Well, that's where things get really interesting. The paper proposes using reinforcement learning techniques to fine-tune these diffusion models. The idea is to treat the denoising process in diffusion models as a series of decisions, where each step of removing noise is like an action in a reinforcement learning problem.
So it's like the diffusion model is learning to play a game where the goal is to create the best possible output?
Exactly. And the score in this game is determined by whatever downstream task or reward function we care about. It could be aesthetic quality for images, or maybe protein stability for molecular generation tasks.
That's a clever approach. But why use reinforcement learning specifically? Are there other ways to fine-tune diffusion models?
Great question, Adam. There are indeed other approaches, but RL has some unique advantages. For one, it allows for more direct optimization of the reward function we care about. Non-RL methods might struggle to generate samples with very high rewards, especially if they're rare in the original training data.
Can you give us an example of a non-RL alternative and why it might fall short?
Sure. One alternative is rejection sampling, where you generate a bunch of samples and only keep the ones with high rewards. But this can be really inefficient if high reward samples are rare. Another approach is conditional generation, but that might struggle to generate samples outside the training distribution. RL methods, on the other hand, can actively explore and optimize for high reward regions of the sample space.
I see. So RL provides a more direct and flexible way to optimize for specific rewards. Now the paper mentions something called entropy regularized MDPs. Can you break that down for us?
Absolutely. MDP stands for Markov Decision Process, which is a mathematical framework for modeling decision-making in situations where outcomes are partly random and partly under the control of a decision-maker. In the context of this paper, they're using entropy regularized MDPs, which add an extra term to encourage exploration and prevent the policy from becoming too deterministic.
And how does this relate to fine-tuning diffusion models?
Well, the paper shows that you can frame the fine-tuning process as an entropy regularized MDP. Each step in the diffusion process becomes a state in the MDP, and the denoising decisions become actions. The entropy regularization helps keep the fine-tuned model from straying too far from the original pre-trained model.
That's a clever connection. Now the paper discusses several algorithms for this fine-tuning process. Can you walk us through some of the main approaches?
Sure thing. The paper divides the algorithms into two main categories. The first is what they call non-distribution constrained approaches. These are methods that focus more on directly optimizing the reward function, potentially at the cost of deviating significantly from the original model.
Can you give us an example of one of these algorithms?
One key algorithm in this category is soft proximal policy optimization, or soft PPO. It's an adaptation of a popular RL algorithm that's known for its stability. The soft part refers to the entropy regularization we talked about earlier.
And what about the other category of algorithms?
The second category is distribution-constrained approaches. These methods put more emphasis on staying close to the original pre-trained model while still trying to improve the reward. One interesting algorithm in this category is reward-weighted MLE.
MLE, that's maximum likelihood estimation, right?
Exactly. This method essentially reweights the original training objective of the diffusion model based on the rewards. It's a nice balance between improving performance and maintaining the properties of the original model.
That makes sense. Now, I noticed the paper also talks about different settings for fine-tuning. Can you elaborate on that?
Of course, the paper breaks down fine-tuning scenarios based on how we have access to reward information. There are three main categories: known differentiable reward functions, black box reward feedback, and unknown reward functions that need to be learned from data.
And I imagine the choice of algorithm depends on which of these scenarios you're in.
Absolutely. For example, if you have a known differentiable reward function, you might lean towards direct reward backpropagation for its computational efficiency. But if you're dealing with black box feedback, you might prefer PPO or reward-weighted MLE, since they don't require learning a differentiable reward function.
Fascinating stuff. Now, the paper also draws some interesting connections to other areas of machine learning. Can you touch on a couple of those?
Sure. One really interesting connection is with classifier guidance, which is a technique used in conditional generation tasks. The paper shows that classifier guidance can actually be viewed as a specific type of RL-based fine-tuning method.
Oh, that's a cool insight. Any other connections that stood out to you?
Another intriguing link is with flow-based diffusion models. The paper shows that the mathematics behind RL-based fine-tuning and flow-based models are closely related, just optimizing different directions of KL divergence.
It's amazing how these different areas of machine learning are all interconnected. As we wrap up, what would you say are the main takeaways or contributions of this paper?
I'd say the main contribution is providing a unified framework for understanding and implementing RL-based fine-tuning of diffusion models. It bridges the gap between several different areas of machine learning and provides practical guidance on when and how to use different algorithms. The paper also highlights the potential of this approach for improving diffusion models on specific downstream tasks, which could have wide-ranging applications in areas like computer vision, natural language processing, and even scientific domains, like biology and chemistry.
That's fantastic, Eliza. It sounds like this paper could be a valuable resource for researchers and practitioners working with diffusion models. Any final thoughts?
I think this work really showcases the power of combining different machine learning paradigms. By bringing reinforcement learning techniques to bear on diffusion models, we're opening up new possibilities for creating more targeted and effective generative models. It's exciting to think about where this line of research might lead in the future.
Absolutely. Well, that's all the time we have for today. Thanks so much for breaking down this fascinating paper, Eliza. And thank you to our listeners for tuning in to ReLU Radio. Until next time, keep learning and stay curious.